a celestial body tracing a hyperbolic trajectory, boasting an extraterrestrial composition, and leaving behind clues that defy conventional explanations. Meet 3I/Atlas, the third verified interstellar visitor detected to date. Fresh findings are shedding light on its nature, and the implications could upend our understanding not only of comets, but of how planetary systems form in the first place. Could 3I/Atlas be a mere cosmic drifter, a seed for new worlds, or evidence of deliberate construction slipping past our gaze? Should any portion of the recent observations prove reliable, it challenges long-held assumptions in profound ways. This marks the starting point for the narrative and the inquiries it sparks. From the era when initial observatories scanned the heavens, each authenticated interstellar interloper has expanded the limits of astronomical possibilities. These are unique occurrences, unpredictable cosmic surprises, impossible to anticipate or replicate, remnants ejected from remote stellar neighborhoods across the interstellar expanse. Yet with 3I/Atlas, the puzzle delves beyond mere path or makeup. Suppose the cosmos isn't merely a backdrop for planetary emergence, but a realm where such bodies are deliberately sown. This concept echoes ancient legends. Today, however, it's teetering on the brink of rigorous scientific scrutiny, propelled by observations that resist neat classifications. The approach here is straightforward. All assertions undergo scrutiny. Every bold hypothesis gets flagged clearly. Verifiable details ground the account. Conjecture remains transparent, never hidden. Whether through molecular signatures, structural traits, or orbital dynamics, the proof will delineate established knowledge from mere conjecture. The implications extend far beyond scholarly interest. If one rogue from a foreign sun bears planetary precursors or traces of purposeful design, our tale of Genesis warrants reevaluation. This isn't a quest for thrills. The threshold for remarkable evidence looms larger than before. A hyperbolic orbit comet is uncommon, yet feasible. An unusual chemical profile might signal an exotic stellar forge or simply reflect sampling quirks from limited observations. The key lies in balancing all with caution. As the probe progresses, avoid dismissing the inexplicable. Instead, evaluate every option, be it random traveler, world-building kernel, or crafted relic, against the accumulating evidence. The process matters as much as the conclusions. Doubt, openness, and the resolve to admit we're still uncertain. In this interstellar cultivation, the true insight might be that all such fragments, organic or otherwise, bear the burden of mystery. The pursuit of 3I/Atlas ignited the instant the Atlas system spotted a swift oddity close to the Milky Way's core, turning the effort into a contest with vast distances and fleeting opportunities. Initial spotting on July 1, 2025, located at roughly 670 million kilometers sunward, embedded in the austral constellations over Chile. Its speed, around 58 kilometers per second against the solar frame, distinguished it from the leisurely procession of local comets. The path, hyperbolic and opposite to the norm, sliced the ecliptic at an acute incline, outlining a route originating well outside solar influence. Retrospective scans from June 14th and later uncovered a subtle, ongoing streak. Ray Chun, sifting the Zwicky Transient Facility's historical records, assembled a chronology extending the object's activity by weeks prior to formal announcement. Progressive measurements refined the ambiguities, enabling trajectory simulations to pinpoint upcoming highlights. A close shave with Mars on October 3rd at 30 million kilometers, then perihelion on October 29th at 1.36 Australian dollars. On December 19th, 3I/Atlas nears Earth to 1.8 Australian dollars, ideal for detailed spectroscopy and isotope studies. By March 16th, 2026, it brushes Jupiter at 0.36 Australian dollars, providing a final shot to monitor its course before vanishing into the distant void. Dr. Maria Fuentes, overseeing the Atlas evening operations, remembered the urgency as the Minor Planet Center hurried to confirm the orbit. Preliminary calculations fluctuated between far-off comet and possible threat. Quickly, though, they settled on clarity, unbound, approaching, and marked as an extrasolar arrival. The route charted, the timeline fixed. Each milestone now probes its elemental makeup, kinematics, and stellar heritage. In 3I/Atlas's surrounding haze, carbon dioxide prevails, overwhelming water gas at nearly an 8:1 margin. This imbalance alone disrupts comet chemistry norms, particularly for those forged in the frigid interstellar voids. Typical inter-system comets seldom exceed a 1:1 balance, and extreme variants rarely surpass it. For 3I/Atlas, CO2 takes center stage. Traces of water, detected via subtle OH emissions, surfaced when Atlas observed from over 500 million kilometers away, equivalent to about $3.5. That's far past the usual solar heating zone for sublimating water ice from the core. Rather, the premature OH emergence points to a crust abundant in easily released volatiles. Or maybe a shell so delicate that remote stellar warmth alone can ignite responses. Far from a dormant fossil, this object stands ready to respond to the slightest hint of heat. Observations from terrestrial scopes and space-based platforms uncover a coma molded by rival influences. An expansive dust plume, wide and directed ahead, enduring steadily, extends from the core, scattering sunlight to suggest sizable, riddled particles hurled away with remarkable effectiveness. Trailing it, a dim tail points opposite the sun, scarcely detectable save in prolonged images. The layout strays far from standard illustrations. The dust plume shines most intensely sunward, a trait commonly linked to comets boasting strong jets or heavily altered exteriors. Still, for 2I/Atlas, this plume holds steady over weeks of scrutiny, resisting the unpredictable flares common among fresh arrivals. Spectral analysis underscores the coma's intricacy. Prominent CO2 signatures flare in the infrared, as customary H2O and CN features hover just above detectability. The dust reddens the backscattered glow, indicating organic-laden or carbonaceous substances. Every reading deepens the enigma. The blend of volatiles and dust setup resists fitting into known types. Rather, they invite probing inquiries. What conditions might craft such an entity? And what insights does its makeup offer into its path? Clear nickel signatures slice through the spectra of 2I/Atlas, whereas iron, typically a steadfast companion in cometary particles, stays notably missing. The VLT team, toiling under autumn's initial evenings, recorded nickel output at roughly 4.6 G/S from $2.85 away. Even as they strained their tools to the utmost, iron's trace evaded capture. The ensuing nickel-to-iron proportion exceeds that of any documented solar system comet. This elemental marker sparks doubts about its origins and evolution. At the same time, the dust's scattered radiance narrates its tale. Polarimetry shows a negative polarization slope steeper than -2.7% at a 6.4 degrees phase angle. Far from a mild decline, it's a steep drop, achievable only by the fluffiest, particle-clumped dust assortments. Lab simulations and computational simulations align on this point. The particles form assemblies of hundreds or thousands of submicron bits, loosely linked in airy, low-mass clumps. Dense exteriors, whether crafted or innate, can't achieve such profound negative polarization absent improbable fine details. The dust reddens the coma's echoed light, pointing to organics and carbonaceous elements intertwined throughout. The core's dimensions stay shrouded. Data from Hubble and Earthbound instruments pin it between 0.44 and 5.66 kilometers. Yet the luminous, dust-laden envelope obscures any precise gauge. Collectively, these traits, nickel sans iron, profound negative polarization, and a core shrouded in peculiar dust, resist simple labeling. Findings accumulate from fields like spectral analysis to optical properties. Each element bolsters the tally of irregularities. The path forward involves probing whether leading theories can endure this mounting array of inconsistencies. Three rival frameworks now dominate the discussion. The initial one, endorsed by many planetary scientists, views 2I/Atlas as a bona fide, albeit chemically turbulent, interstellar comet. Here, the elevated CO2 to H2O levels, prompt O emission start, and steep negative polarization curve all signal formation in the chilliest zones of a foreign star's birthplace. The loose, clumpy dust matches decades of lab replicas and polarization frameworks. To these proponents, each peculiarity offers an opportunity to expand comet classifications without resorting to the exceptional. The next idea, proposed by experts like Dr. Nina Alvarez, posits 2I/Atlas as a planetary embryo, a core expelled from a nascent system bearing isotopic echoes of its genesis. Should such items get snared by forming disks often, they could clarify rapid gas giant assembly. Alvarez highlights prospects for alien isotopic mixes, cosmic dispatches in vessels, as the crucial verifier. Efforts to detect these markers have sparked intense rivalry for JWST and ALMA slots, with proponents wagering one offbeat ratio might overhaul planetary buildup chronologies. The final, bolder notion regards 2I/Atlas as a concealed relic or perhaps a bioengineered entity designed to resemble a comet. Avi Loeb, a steadfast advocate for thorough open inquiry, stresses that peculiarities by themselves fall short for artifact claims. Proof demands a tougher threshold. Ongoing baffling speed-ups, ejection flows flouting laws, or spectral marks too hard to simulate. Anything milder, he warns, merely reflects the cosmos's untamed nature. This isn't coincidence, it's just data, devoid of purpose. Every hypothesis requires its own validation, and upcoming observations will determine which narrative holds up under scrutiny. All competing ideas must pass the same rigorous scrutiny. Proof demands not only adherence to physical laws and statistical rigor, but specificity. For 3I/loss, mere scattered data points or an anomalous reading won't suffice. The threshold for evidence is elevated and precise. A consistent acceleration without gravitational origins, one unrelated to venting or solar radiation pressure, would demand a reevaluation. Comets, however, are infamous for faint influences from sunlight. Only sustained, unexplained deviations observed over multiple weeks and compared to all established emission models would qualify as genuine outliers. Chemical composition, likewise, requires verifiable replication. An inexplicable elemental proportion or a spectral feature impossible to replicate in labs would trigger further investigation. Still, the annals of cometary studies are rife with misleading clues, spurious signals from equipment, overlaps from ambient sources, miscalibrations that simulate the unusual. Hence, every assertion undergoes verification by separate research groups employing varied observatories and data processing methods before entering the catalog of anomalies. Statistics serve as the impartial arbiter. Given just two previous interstellar visitors, Oumuamua and Borisov, each newcomer could easily be an outlier rather than typical. After-the-fact probability pitfalls are plentiful. An unusual orbit or uncommon makeup might seem compelling alone, but often diminishes when viewed amid the immense, largely unmapped interstellar catalog. The field's ethos is to avoid premature conclusions based on scant details. Bold assertions, whether remnants of technology, primordial planetary fragments, or peculiar comets, necessitate not merely a trend, but one that endures against all rival interpretations and critical examination. The timeline now hinges on 4 key milestones, each a milestone in unraveling the mystery. On October 3rd, the object makes a close approach to Mars at 30 million kilometers, a tantalizing brush with the red planet. As of late September, however, the ESA's Mars Express mission hasn't announced intentions to redirect for targeted views of the comet. Should a sudden adjustment occur, it would first appear in formal announcements. Meanwhile, attention turns to terrestrial observatories. October 29th signals perihelion, when 32/Atlas reaches its nearest solar distance of 1.36 astronomical units, slightly outside Mars's path. This phase amplifies activity levels. Earthbound observers will monitor chemical changes live, probing for abrupt variations in gas outflows or particulate ejections. The enigmatic coma could unveil additional complexities under solar heating, offering a glimpse into evolving reactions timed by celestial mechanics. December 19th represents the optimal observation slot. Position 1. 8 astronomical units from our planet. The comet aligns with the James Webb Space Telescope, Hubble, ALMA, and the Very Large Telescopes fields. Dr. Leah Morgan heads the JWST effort to assess isotopic abundances: deuterium to hydrogen, carbon, 13 to carbon, 12, nitrogen, 15, oxygen, 18. These ratios, determined to 4 decimal places, might resolve debates on origin and formation. Each observatory contributes uniquely: JWST for organic compounds and isotopes, HST for coma morphology, ALMA for subtle gaseous emissions, VLT for particulate and metallic content. Observation schedules, intensely debated, generate data streams around the clock. March 16, 2026, closes the sequence. The comet glides by Jupiter at a mere 0.36 astronomical units. High-precision positional measurements from Paranal and Mauna Kea teams will seek evidence of atypical influences that defy standard gravitational models. Should a concealed propulsion or directed emission exist, this encounter might expose it through the metrics. The resolution remains uncertain, the evaluation in progress. At present, the tail rests with skywatchers and interpreters poised for incoming insights. All trajectories from 3I's/Atlas stem from one root: empirical data. The possibilities aren't a web of conjecture, but a chart guided by cosmic measurements. If the composition remains consistent, with carbon dioxide exceeding water vapor and isotopes linking to remote, frigid origins, the conclusion points to a bizarre, yet native comet, enriching the roster of familiar celestial bodies and expanding cometary frontiers incrementally through each reading. If the isotopic signatures diverge from all inner solar system norms, hydrogen, carbon, nitrogen, oxygen all misaligned, the fragment from a planet theory strengthens. A signature from elsewhere, enduring billions of years across void space, could transform insights into gas giant formation. Every ratio, precise to 4 decimals, acts as a dispatch from a foreign stellar cradle, hinting at the mechanisms behind world building. Alternatively, if the data defies alignment, if the trajectory strays beyond solar or outgassing effects, or if spectral signatures emerge beyond natural origins, the wildest hypothesis prepares for validation. The standard for technological relic or biological entity stays extraordinarily demanding: replicable, hardware verified, and impervious to deception. NET absence of proof brings clutter, not clarity. Across each pathway, the approach remains steadfast. Assertions are measured, not merely hoped for. Doubt serves as an instrument, not a barrier. The narrative surrounding 3I/Atlas isn't a battle of fanciful speculations, but a methodical ascent toward verifiable truth. Ultimately, the cosmos responds solely to inquiries posed with rigor and restraint. Upcoming viewing periods: October alongside Mars, December originating from Earth, and March via Jupiter. Stand ready to collect information that might validate or dismiss various possibilities. Given only 3 documented interstellar visitors, each piece of data carries weight. The facts call for caution, yet also vigilance. The resolution could broaden or fundamentally reshape our grasp of planetary formation and, perhaps, the emergence of life.